Hi guys, and welcome to Mindset Learn Extra. This is grade 12 science. Tonight's show is brought to you by Liberty, and last week we covered power with Philip. Tonight our topic is photoelectric effect, and Phil will be taking us through it. Hi Phil.
Hi there everyone. Okay, welcome back to the show, and I'm going to be taking you through Einstein's work, and we're going to be talking about photoelectric effect this evening.
Yeah guys, so it's going to be fun. Please make sure that the questions that you do paste onto our wall have to do with the topic that we are talking about. Guys, throughout the year we will eventually get round to the section you are having difficulty with, so please be patient. So, without further ado, I think what we're going to do is that we're going to go to a short break, and as soon as we get back, I'll go through everything you'll need to know about the show and everything you need to know about what's happening next week. So, see you now after the break. Hi grade 12s, and welcome back to Learn Extra Live. Tonight our topic is photoelectric effect, and Phil will be taking us through this. So guys, please make sure that you send the questions relating to this topic and put them on our page, and eventually we will get round to the section you are having difficulty with. Guys, next week our topic will be organic molecules. Lots of you have been asking us about our schedule. So if you are in a group, the next week's topic is organic molecules. The show tonight will start off with the lesson on photoelectric effect. Then after a break, we'll work through an example or two. Then lastly, we'll tackle your questions on the topic. There are lots of ways to get hold of us. One of the ways is on Facebook. It's facebook.com/learnextra. Our Twitter handle is @learnextra. So while you're watching, shoot us questions and we'll get round to them in the third part of the show. I have a Casio calculator to give away tonight. It's one of the best posts on Facebook. We will be announcing the winner tomorrow on the Facebook page. So without further ado, I think we're going to get straight to Phil.
Thank you so much, India. As was said, we're talking about the photoelectric effect. And the photoelectric effect is something that often only comes up later on in the year for matrics. But one of the things that you can do tonight is I've tried to set up the lesson so that you can take notes and actually learn it from scratch, so this should be useful. Whether or not you're watching it live, or you're PVRing it, or you're watching the highlights package, no problem. What I'm going to be doing is I'm going to be taking you right through the photoelectric effect and see where it goes. Well, let's go right back to the beginning, as is a good place to start. One of the things that I thought I would show you is where the photoelectric effect actually came from. Okay, the guy in the picture, most of you will know him, Albert Einstein. He won the Nobel Prize for a paper which he wrote in 1905. What he actually managed to figure out was why certain things were happening. This guy managed to figure out that light was a particle which carried energy. Now, that may not seem like a big deal, but he actually managed to figure out one of the major puzzles which was happening inside physics. He managed to figure out that light was traveling as a wave and as a particle. Now, not many proofs for particle existence had come along until this 1905 paper, and this is what won Einstein the Nobel Prize. So what we're going to do is we're going to take a look at the 2 points which he came up with in his famous paper. He told us that photons are the particles of light and that they contained energy called quanta, if you want to write that down. And if the photons contain enough energy, they can free electrons from atoms. Now, I've got a great video clip a little bit later on. We're actually going to show you that electrons can come off, and we can actually physically see electrons leaving something, and this is a very nice graphical way of representing it. Okay, so how does the photoelectric effect actually happen? I'm going to break it up into a few steps. We're going to talk about the light particles coming in. We're going to talk about the way that they interact with the surface, and eventually we're going to have the ejection of electrons, but we'll come to that in a little bit. Okay, so let's start off with a challenge. Now, for those of you that are working with us, we're talking about the photoelectric effect. I'm going to use a light of 100 nanometers shining onto a surface of 4.3 electron volts. Now, that's a reference to its work function, the W0. Its work function is 4.3 electron volts. Now, that's zinc. Now, the reason that I've used zinc is because it's the same one that we've used inside our clip, and you can actually see what's going on. So I've got 100 nanometers, which is UV light, ultraviolet light, and it shines on a surface of 4.3 electron volts, and that's a reference to its work function, how much energy is required to release electrons. If you're not sure what I'm talking about, it's okay. I'm going to explain it in bits and pieces. So I'd like you to take this challenge question down see if you can post a couple of answers on our Facebook page, maybe Twitter them through, and we'll see if any of your tweets are correct. So 100 nanometers is our wavelength of light, 4.3 electron volts is the work function, and I want you to calculate the velocity of the ejected electrons. So there's a couple of pieces to this. I'm going to break this down into 3 steps when you start to take a look at the photoelectric effect. A lot of equations involved and a lot of complications. So while you're busy taking this down, what I'm going to do is I'm going to break it up into those 3 parts. I have the light arriving, which was 100 nanometers, that UV light shining on the surface, the work function, and then eventually the kinetic energy which comes off in the velocity of the ejected electrons. All right, fantastic. I hope that you're working furiously away at that. If this is a new section, just wait for the show and we're going to work your way through it. Okay, so let's jump into how this actually happens. All right, well, I've got my light which shines on a surface. Now remember that Einstein managed to explain that these photons of light, these packets of energy of light which shine down, can be quantified. This means that I've got an amount of energy which comes with the light, and it comes in these little packets. The way that we can calculate the amount of energy inside them is using something called Planck's constant. And I've shown it on the screen here for you. 6,63 times 10 to the minus 34 joule seconds. That's a constant which is given to you during the exams. And if I multiply that by the frequency of the light, we can actually calculate how much energy that light has got. I just want to pause on that for a little bit. Planck's constant multiplied by the frequency of that wave, we can actually figure out how much energy this particle is actually delivering to our metal surface. Now we've got our electrons down at the bottom here. Remember, we're talking about the photoelectric effect. Photo, reference to light, and electric, we're talking about electrons which are moving. So what we're going to do is we're going to see how electrons come off the surface and where do they go once they've left the surface. Well, let's take a look at the next part. Well, once the electrons have gained this energy, the photon of light has gone in there. You can see that my electron is busy moving off the surface. This W0 is the work function. This is how much energy. Remember, I told you a little bit earlier on that zinc's work function was 4.3 electron volts. This is what I'm talking about. Work function is W0. And I've got W0 here, which is the energy required to pull this electron up to the surface. Now that requires a lot of energy, and that's the work function. So some of the energy which comes in is used to free the electron. Question is, how do I actually figure that out? Well, this is coming from the frequency of the light. Remember, I told you that you could calculate the amount of energy by taking h times f, Planck's constant multiplied by the frequency. I call the minimum frequency that I need to eject these electrons from the surface, I call this my threshold frequency. And the way to calculate it is here. My work function is equal to Planck's constant multiplied by F0, which is the threshold frequency. So one of the things that you can do is you can answer questions now about work function and threshold frequency. If I gave you the work function, you could calculate the threshold frequency. If I gave you the threshold frequency, you could find the work function. All right, now the threshold frequency is actually a really, really important thing because this tells me the minimum speed at which photons have to vibrate, or these waves rather, have to vibrate to free electrons from a surface. Now there definitely is a cutoff point. This word threshold means that there is a cutoff point. Now if I exceed that cutoff point, that means that I allow electrons to leave the surface. And what we're going to do is, in one of the slides which is coming up next, we're going to take a look at a video clip which actually shows us this in effect. But before I do that, what I'm going to do is I'm just going to show you where the electron goes. I've had my photon of light coming in, the electron has absorbed energy, and the work function has been used up, that amount of energy has been used up to free the electron, and now there's extra energy, which is K, standing for kinetic energy. What we're going to do is we're going to show you a short video clip of electrons being freed by UV light. Now, I want you to take a look. What the professor is going to explain to us is how much energy is required is actually shown by the frequency and wavelength of the light which he uses to shine on the metal surface. We're going to take a look at that video clip right now.
Well, in 1885, round about that period, a very interesting discovery was made by Heinrich Rudolf Hertz, the man who in fact proved the existence of radio waves. What he also did was he found an effect known as the photoelectric effect. And in our laboratory today, we can actually show a very simple experiment, a very classical experiment, if you like, on this particular effect. Here we have a typical gold leaf electroscope, and I'm sure most of you have seen gold leaf electroscopes in your time, but just to give a brief explanation, what happens is that if I charge the gold leaf electroscope with some electrical charge, a static charge, be it positive or negative, the gold leaf within the glass enclosure here will simply open up to indicate to us that such a charge exists. Now, what we're going to do is I'm going to impart upon this electroscope a negative charge, and for that I've got a nice piece of fur here and a glass rod, and we'll simply rub this rod thus, and with a bit of luck, and in a lot of cases physics experiments tend to fail, but let's hope that this one works quite nicely. You will see now that as I bring the rod to the electroscope, the gold leaf stands out very proud. There we are, we've got a nice charge on there, and that hopefully is a negative charge. Now, first of all, let's expose that negative charge, if you like, and our zinc plate. I'm going to expose the zinc to ordinary white light. There we go, from a good old torch, and as you see, absolutely nothing happens. Let's see if it has anything to do with the intensity, because it might well be. For this, I've now got one of these really high intensity lamps used in filming, as we have in the studio, and there we go, we switch it on. I've now applied a large amount of high amplitude, if you like, high brightness white light, and still nothing happens. Let's now put the ultraviolet light in place, and look what happens. Your gold leaf discharges. You can actually see the gold leaf dropping from the near horizontal position back to the vertical. Now, I imparted onto the zinc a negative charge, electrostatic charge. When we exposed the zinc to ordinary visible light from this torch, nothing happened. The gold leaf tended to stand out, and as we applied the light, nothing occurred. It stayed put until we put this shorter wavelength source of light, this ultraviolet light, which is at around about a wavelength of about 390 nanometers, if you like. We placed this, the source of light close to our zinc plate, and what in fact happened was that photons, very high energy photons from the ultraviolet source, struck the zinc plate, and thus knocking off electrons. And so our negatively charged electrons were released, and of course discharging our gold leaf electroscope.
Wow, fantastic. Thanks so much for that, Prof. I hope that you saw inside the video that he actually explained that if light has a short enough wavelength, and I hope that you remember from grade 10 that a short wavelength means a high frequency, that we've gone over the threshold frequency. We've got enough energy to get past the work function. And that's exactly what was happening inside the video. I had all these electrons nicely lined up on the surface of that electroscope, which was zinc, and it's zinc inside your work-through example, and I've got the electrons actually leaving the photoelectrons actually leaving this electroscope. And we can actually see that because the leaf went down, the leaf discharged, showing us that electrons have actually left because of the UV light. Something else which was important to show was then when he was using a lower frequency, in other words, that white light from the torch, that nothing was happening. The frequency was too low, and this is a great example of something that they can ask you in an exam. If the frequency is too low, no photoelectrons will be ejected from it. So what we're going to do is I'm going to let you work through that challenge question, submit your answers to India on here, and we're going to take a look and see if you guys can work through some of the complex calculations involved in the photoelectric effect. But right now, we're going to take an ad break.
Hi guys, and welcome back, grade 12 Mindsetters. I hope you're enjoying the show. A whole bunch of you have been writing in and giving answers to the challenge question. I know it's quite tough, but don't worry. Phil is with us and he will be taking us through it later on. So guys, don't stress. There's no such thing as a wrong answer. Just post, and that's the thing. If you get it wrong, you learn from it, right? Okay, Phil, straight back to you.
Okay, mindsetters, what we're going to be doing is I'm going to be taking you through the mountain of equations which are on your equation sheet. I'm going to show you how to use them, how to pick the right one, because a lot of people say, oh, I don't know where to start. Okay, so I've listed a couple of the equations. I'm going to write them out with you, and we're going to see exactly what goes on here. Remember what I talked to you about, and I'm going to take a little bit of time in explaining these. If you want to write them down, it's entirely up to you. I'm going to be taking them down one by one. I'm going to be highlighting the important bits as I speak through them. Now, the first and most important one is that the energy of the photon is what goes in. Now, where that energy of the photon goes is entirely up to how much is used on the work function. So let's just highlight this as we go, because there's a lot of information here, and I want to make sure that people can follow, even if they haven't done this section yet. So I told you that the energy of the photon, this is the energy of the light which is going in. I've got on the other side where the energy goes. I've got the work function is how much energy it takes to pull the electron off, and what's left over is how much is left over for kinetic energy. Now, you can change this equation exactly to suit your needs, and there's two major forms that I found. I found that energy of photon, because E is equal to HF of a photon, that's the basis of this, that if I find the energy of a photon, I can find it by saying Planck's constant multiplied by the frequency. So that's the energy which is going in. Where does the energy go? Well, it goes towards the work function, and you might recognize this before from grade 10, that kinetic energy is equal to half times by the mass times by the velocity squared. Now, this one is really, really tricky, because remember what you're doing is you're talking about the mass of an electron, and that should be a big hint towards solving our challenge question tonight. The mass of an electron is the mass of the object which we're actually accelerating. We can't talk about accelerating the surface, we don't know how heavy it is, but this is definitely that mass of an electron. Okay, well, now we know that K stands for the kinetic energy of these electrons. We're working our way through these. We know that energy of our photon is equal to HF. We use up our work function, and we're left with kinetic energy on the other side, and that's a half multiplied by the mv squared. So I know that I've got work function, and I've got the kinetic energy over there, and that actually tells me how fast my electron is going. So if you're on this path, fantastic. The problem with what I did was I gave you not the frequency, but I gave you the wavelength. So the form of the equation which I'm going to use uses a little bit of grade 10 wave stuff, and never forget it. Go back and revise. That the velocity of a wave, in this case c, which is the speed of light, is equal to frequency multiplied by my wavelength. C is equal to frequency times lambda. Remember that that applies for any wave which is electromagnetic. That applies to light waves, to radio waves, to microwaves, infrared, even UV, which is our challenge question. So I've got my C, which is equal to speed of light, is equal to frequency times lambda. You don't have to go and find the frequency before you do your photoelectric. What I've done for you is I've shown you the formula when we've combined it all. I've swapped out frequency for C over lambda. I'm just going to highlight what I mean by that. A lot of people are going to get a little bit confused here. C over lambda is equal to frequency. That's all that I've done in that equation. So H times by frequency, in other words, C over lambda, which is way more useful, is equal to my work function plus a half times my mass times velocity squared. Something else which is going to bother a lot of learners at home is how to work with electron volts. I'm finding that a lot of people say, work function, fantastic, you gave it to us, it was 4.3 electron volts, I'm going to substitute it in there. You cannot. And I'm pretty sure that a lot of people on the Facebook page are actually saying, what is 4.3 electron volts? That's one of the things that I'm fairly sure that's coming through. I'm finding that C over lambda is equal to work function, and my work function has got to be in joules. I'm not sure if any of the viewers at home have started answering. Have they, Indy?
They have indeed. Would you want answers?
Well, not quite yet.
Not yet. You just want to know if they're listening.
Absolutely.
Okay.
I want to see if people are asking questions, what they're confused about, and we're going to move on from there.
Okay, guys, if there is anything that you are confused about regarding the question, let me know now, so when we do answer the question, we can go over it with Phil.
Fantastic. And
Cool.
that'll be answered in our third part of our show.
Yes, exactly.
Okay. Fantastic. Okay, so we're getting back to this. We've identified which one out of these three is most suitable for our answer. Well, I've got the speed of light. I always have h, which is Planck's constant. 6,63 times 10 to the minus 34. That was given earlier on in the show, and it's always on your information sheet. So c, 3 times 10 to the 8 meters per second, which is the speed of light. Another constant which is given to us, the wavelength, which was 100 nanometers. Now please don't substitute 100 in there. I'm going to show you why in a moment. My work function, can't substitute in the electron volts. Remember, this is a challenge question. A lot of you are not going to get this correctly. I've got my mass of an electron. So each one of these is going to require you to think heavily. I want you to use this equation, and we're going to work through it together. One of the big hurdles that you're going to find is using electron volts. Now, not all of you have to do this during exams, but I'm going to show you how to change from electron volts into joules. And then we're going to get on to the actual solution for our question. If I take electron volts and I multiply by the charge on an electron, I get back to joules. That's quite an important thing to know. The reason that I do this is 4.3 is a much nicer number to deal with than the actual amount of energy. The amount of energy is so small, so minute that I can't actually work with it. The amount of joules is very, very small. So let's actually take a look and see how the conversion worked. If I take a look here, I've got 4.6, apologies, sorry there, 4.6 times 1.6 times 10 to the negative 19. We've got our conversion back into our joules. So I'm working with 4.6 electron volts here. I multiply by the charge on an electron, and I'm changing it into joules. I hope that everyone can see that. 4.6, I've multiplied by charge on an electron. That will get me into the joules. Now let's use our information here, and let's work forward. Okay, so I've got my original equation. I've broken it up into two pieces because they're so large. I could take this and put it back on there, but you can see that that doesn't fit onto the screen. So I hope that you'll bear with me that it actually does fit onto the screen when we break it into two parts. Okay, so I take my Planck's constant. 6.63 times 10 to the minus 34. There it is. I take my Planck's constant. Now, what I'm going to do is I'm going to substitute in the speed of light, which is c. So 3 times 10 to the 8. Here's our wavelength. A lot of people don't know to do this. 100 nanometers. If I take 100 nanometers and I put it in there, what I'm going to find is that 100 nanometers over here is going to give us 100 times 10 to the negative 9. Nano means times 10 to the negative 9. And that's something a lot of people don't actually know it yet. Here's our work function that we worked out over here. I've got my work function here, and let's just move it over, make sure that everyone can see it at home, right? Because I think I'm fairly close to the side here. I've got 7,36 times 10 to the negative 19. Let's just move over our highlighting because that should actually fit in there. There we go, right? And that's the amount which I substituted inside there. And I add to this a half times, and a lot of people don't know where this number comes from. This is a number which people don't actually know that they've got. I've got my electron volts changed into joules over here. This is the other constant which is given to you as the mass of an electron. 9,1 times 10 to the minus 31. And that's kilograms. This is how small an electron is multiplied by V squared. That V is what I'm after. So if I take 9.1, sorry, let's just make sure that we're highlighting there. Let's just move that off. All right, if I take 9.1, 1 times 10 to the minus 31, and I multiply that through and I start solving, I'm going to show you how to manipulate this because this maths is very, very complicated. I'm going to show you the fully manipulated part, and we're going to see. So on my next slide, I've done exactly that for you. All right, so I've blown it up nice and big. So what I've shown you is that I've got my fully worked out answer on the left minus my work function over half times my mass of my electron. And that was equal to V squared. So that was my manipulation. I found V squared on its own. The only thing which I've got to do left is actually to find V. And I've got to find V by square rooting the whole lot. Now, some of you might find a slightly different answer to this. And most of the reason behind that is because of rounding halfway through. Some of you have kept it in your calculator, some of you haven't. That's no problem. If I put it in as such, I'm going to get a velocity of this, and we're going to find a velocity in excess of 1,000,000 meters per second. That's unbelievable. Very, very fast. Okay? So this is starting to get like into physics breaking territory, and you'll actually find that electrons don't really do this in real life. What happens is as they start approaching the speed of light or exceeding it even, which is not actually possible, they'll start getting heavier. This mass won't actually apply anymore. I want to see if any of the viewers at home have managed to get an answer similar to this one.
Okay, well, let me have a look. I'm going to be honest with you, Phil, here, but don't be upset, because it's got
That's
nothing
okay.
to do with your teaching.
Okay.
A few of the learners are a bit confused, and
That's
I was wondering
okay.
if I could ask you a few questions regarding to this question now,
Absolutely.
before we move on. Let's see. Drew wants to know, what is C?
Ah, very good question.
Yeah.
Okay. All right. We did explain it very briefly early on, but I kind of assume things, and you can never assume things. Okay. I'm going to go back to C. Let's actually make a little bit of space down here at the bottom. Let's explain what C is, because that's a value which people don't actually know about. The reason that I used it was that I had C is equal to frequency of a wave times by lambda. Now, C was the thing that people weren't sure about. The equation that people are used to from grade 10 is actually V is equal to frequency lambda. Now, why have I chosen to take C in place of V? Well, C is a particular velocity because V stands for velocity. Now, in this case, this is the speed of the light waves. So this is the speed of light, and that's a constant given to you on your equation sheet, which is 3, 0 times 10 to the power 8 meters per second. Now, that is an unbelievably high speed, but remember, we're talking about the speed of light. This speed will get you 7.5 times around the world in 1 second. It's unbelievably quick. Even at this speed, it takes 8.3 minutes for light rays to get from the sun to us. Something else very interesting, something which I like to give people as a challenge, is how far away is the sun from us if it takes 8.3 minutes, in other words, 8 minutes and 20 seconds to get you at this speed. Something that you can do if you're looking for a little bit of time and a little bit of a challenge. I hope that answers that question.
I hope so too, Phil. Okay, here's another one from Sophia. Why can't we use the NM as 100? Why not?
Sorry?
It says why we can't use the NM as 100. Why
Oh, the
not?
nanometers.
Yes.
Okay,
yes,
fantastic. All right. Very good question. This is one of the problems that we actually bump into a lot when we're working with photoelectric, when we're working with our light waves. I'm going to talk to you about this guy, lambda, which is our wavelength. I told you earlier that lambda was equal to 100 nanometers. If I've got 100 nanometers and I'm substituting it into this equation, something which you'll notice, especially in your constant C, and I'm going to highlight this because this is very, very important. My speed is in meters per second. I cannot work in nanometers. This is why I cannot use the nm or nanometers. What nano means is 1 billionth. I could take 100 and divide it by a billion, but that's a real pain in the butt. So what I'm going to do is I'm going to take 100 and I'm going to use times 10 to the negative 9. So let's give ourselves a little bit of a space there, and let's actually work our way through there. So instead of saying 100, I cannot use 100. Let's use 100 multiplied by 10 to the negative 9. What that does for us is it makes this into meters. And remember, because I've got a speed in meters per second, I've got to use a wavelength which is in meters, and that's why I can't use that. So that explains where C came from and why I can't use nanometers. Very, very important. Now, this is something people have probably forgotten from grade 10, but I've got to work in SI, or Scientific International Units.
Okay, here's another one from Maro Ping.
Good.
How do we get the mass of the electron?
Ah, very good question as well. A lot of people are asking about these constants. Now, they're not very familiar to you. I want you to look for the following thing. If you find on your equation sheet, this is the one that you're going to look for. Right, let's just make sure that we can write on there. Sorry, let's just move that out of the way. So, if I've got a mass of an electron, oh, we're struggling there. I actually want to show you the mass of the electron. There we go, the mass of an electron. This is something which is actually a constant on your equation sheet. The mass of an electron is a known mass. It does change with the speed, but I don't want you to worry about that. Is that the mass of an electron is 9,11 times 10 to the minus 31 kilograms. That is the mass of an electron. This is given to you. Either it's in the question or it's on your data sheet, but this is a constant which you should be used to and they should actually give to you. This is something which I need if I'm going to find the velocity of an electron.
Fantastic. So guys, what I think we're going to do is that we're going to take a short break, and as soon as we get back, Phil's going to go over a little bit more work. I know we've got a few more burning questions, so I'll pull Phil in during the break and we'll see what's important. Guys, keep those questions coming. We're loving it, and I'm loving the fact that you guys are helping each other out on the page. I think that's fantastic. And now for a little break, and we'll see you in 2. Hi guys, and welcome back. What we're doing right now is we are still talking about the challenge question that we posted on the wall earlier. Guys, don't panic, because a lot of you are screaming on the page that you don't know what's going on. Just relax. Also, sit down on the floor and take a deep breath, because Phil is going to help you. Please let me know if there's anything that he's not, and maybe you're not, he explains things fantastically, maybe that you're not understanding correctly. Let me know on the page, and I'll stop Phil and I'll ask him. Guys, this is your page, so get those questions in. Phil, over to you.
Thanks so much, Indiana. Okay, I realize that there's a lot to carry on, especially if you haven't done this at school, and that's a lot of you guys. So what I'm going to do is I'm going to go from the equation, which you do have already. This is on your data sheet, and I'm going to explain the little bits and pieces. A lot of people are saying, okay, well, the substitution is the place where I'm so lost, so I'm going to do it in bits and pieces, and we're going to get there eventually. So I'm going to start off with a basic photoelectric equation, and we're going to see from there. Now, the electron volt one I threw in as a real challenge. I don't expect you all to be able to do that. This working out our electron volts for our work function, or for our minimum amount of energy required to free the electron, I don't expect you to be able to do that yet. But what I'm going to do is I'm actually going to leave the left-hand part on its own. So I'm going to be dealing with this equation. I'm going to be dealing with H and C and lambda. Let's just deal with that part of the equation. So what I'm going to be doing is I'm going to talk about this little piece over here. Let's actually highlight it, and let's talk our way through the substitution in this. There's a lot of people are kind of, their heads are spinning because they haven't done this yet, and that's okay. So what I'm going to do is I'm going to go right back through this, and we're going to see if we can't figure out how to substitute this. Well, H is a value which comes off your equation sheet. This is called Planck's constant. They actually show you the symbol H, and this is it. 6,63 times 10 to the minus 34 joule seconds. That's the value that I'm looking for. C, as I explained a little bit earlier to one of our viewers, C is another constant. This is the speed of light, and if I look down at the bottom, lambda is another problem for a lot of people. 100 nanometers, I can't leave it like that. I've got to say 100 and make it nano. Nano means 1 billionth, or times 10 to the negative 9 meters. So I've got my H substituted, I've got my C substituted, and I've got my lambda now substituted. Now I'm going to shift my attention to the right hand side. So let's actually move that down there. Let's move the box with it. Right? Let's actually wipe that out. Let's make our page nice and clean, and let's work with this. And let's actually see if we can't figure out what's going on the right hand side. So I'm going to use a different color there. Let's see if we can't highlight this in a separate color here. I hope that you can see that at home. Now, I'm going to pay attention to the right-hand side of this equation. I'm going to do it here with you. Let's actually shift it up underneath, and we're going to pay attention to how we actually do this. So my work function, remember that was the part which actually told me how much energy was required to free the electron. That was the amount which was required, and some of you might have slightly different rounding numbers, and that's okay. So if I take my work function over there it is. If I take 7,36 times 10 to the negative 19, that's a measure in joules. That's the amount of work which is done to free the electron. In other words, to pull it off the surface. But what happens if we put in way too much energy? There's going to be a whole bunch of extra energy that needs to go somewhere. And that's given to our kinetic energy. My mass of my electron, that's where it goes. I've got my m going in there as 9.11 times 10 to the negative 31. Somebody actually asked me, what is the unit for this mass? Now, we're working in physics here. When you work in physics, the masses are always in kilograms. If you're given in grams, it's got to be in kilograms. If you're working in chemistry, however, when you're working with moles, that's the only time that you're going to work with grams. In physics, we're going to stick to kilograms. And this is a value which is given to me off my equation sheet. Now, I told it to you earlier, but just for reference, if you're worried about what to look for, this is the mass of electron, and this is the way that it's actually shown on your equation sheet. 9,11 times 10 to the negative 31. So a half times by that mass times by the velocity of this electron. Now that is an unbelievable velocity. So if I do all of the substitution and I find V, which is a lot of maths, I'm going to find out that my velocity right at the end is well in excess of 1 million. I hope that answers the questions.
I'm sure it does. Okay, I know that there are a few more. Are you ready?
Absolutely.
Okay. Okay, Tumelo says, we did this stuff and I kind of understand them, but where does that work function come from?
Okay, where does the actual work function come from? Okay, well, we're going to deal with that. That's part of the equation, and this is part of the difficulty in understanding this.
Okay.
So I'm going to run you through a couple of the steps once again. We're going to draw out some of the pictures. I'm going to try and get you to picture this inside your head. It's very difficult to picture photons of light and electrons flying around if I can't directly see them. So what I'm going to do is I'm going to represent this in a couple of ways. So I have my photon of light. The waves are going to strike the surface with the energy, which is the energy of the photon, which is E is equal to HF. That's the amount of energy which is coming in. My little photon is going to fall on the surface with all of my electrons. So here is my lucky electron. It's going to receive the HF. The energy is coming in from my photon. That energy that I can calculate by saying that E is equal to Planck's constant times by the frequency. Just remember that there are variations on that. I can also calculate the energy of that photon by saying the following. I didn't give you the frequency in the challenge question, so what you could do is say that E is equal to h times by the speed of light over lambda. These are two very acceptable ways of calculating the energy of a photon. So now I've got the energy of the photon which is coming in here. Now to answer the question, I want you to think of the reason that the electron is inside there. If you've been watching some of our grade 10 and 11 revision sessions, we've been talking about bonding inside metals. Metals have got electrons which can move. Now this electron itself can actually move. I just need to give it a little bit of energy, give it a little bit of push, and that's where this energy comes from. The energy of the light is giving its energy to the electron. I have to do work in order to pull this electron off the surface. So if I want to actually move this electron and actually move it out of the metal onto the surface, the amount of energy which I have to do, or have to give it, in other words, is called the work function. So that work function over there, let's make sure that you can see this. This is called the work function. Now, let's just make sure that we're writing in a visible color there. That is the work function, or W0. 0 just usually means that it's the standard value. Now, for zinc, it's anywhere between 4.3 and 4.6, but we actually free this electron to come up to the top, and that energy that's required, the work that we need to do, is actually called the work function. Electrons are in there with a great amount of force. I actually need to pull them out, and the way that I do that is using light energy. I hope that answers that question. Are there any more?
Okay. Dare I say yes? Let me see. Musa says, who is a Constance? Does that make sense? I'm not Constance. My name's Indiana, Musa.
Okay. All right. Well, Constance is a girl's name, but we're talking about constant. Okay. So
not my spelling error, Phil.
Oh, no, absolutely not. Okay. Right. But it's an easy misunderstanding, especially for somebody that's not hearing me correctly, or I'm pronouncing this way too quickly. So let's just make sure that we actually figure out what we're talking about. When we talk about Planck, and Planck is actually spelled kind of weird. When we talk about Planck's constant, which is 8, which is P-L-A-N-C-K, which is really weird. Planck, because this is the name of a guy. Unfortunately, this is his name because this is a really, really odd name. I feel sorry if anybody out there has got this name. I feel sorry that I've offended you. Okay, but H is equal to Planck's constant. Let's just make sure that we're talking about the correct constant. We're not talking about a girl called Constance. Okay, so we're talking about wait a minute, we're actually misspelling there. Let's just make sure that we're getting this right. Okay, so we've got con, which means, there we go, which means with. Okay, so constant, which means that it stays the same. Planck's constant is the same in all chemistry. Whenever we talk about Planck's constant, we talk about a value which is 6,63 times 10 to the minus 34 joule seconds. It's given on your equation sheet. It's one of the constants.
Okay.
Let's just make sure we put that T in there.
Yes, the T,
Okay.
not the Constance. Okay, Kaklejo is saying, Wusa, relax. Good job, Kaklejo, I told you. Okay, and Nelly says, are we going to substitute the electron mass into kinetic formula? A bit
very
confused.
good question. Okay, all right, let me just go back to the original photoelectric equation, the very, very basic one, and let's just make a little bit of space there, and let's see if we can't sort of clear up that confusion. Are we going to put the electron mass inside kinetic energy? Absolutely. So if I've got my energy of my photon, remember that goes on the left-hand side. I do a little bit of work, which is my work function. This is the question. Here's my kinetic energy. There's K. So what I'm going to do is I'm actually going to substitute. I'm going to put something different in each one of these. The energy of the photon, remember, was h times by f. My work function, which was there, which we explained a little bit earlier, there it is, and we substituted that in. It's got to be in joules because we're talking about work, and work is a transfer of energy. We measure that in joules, but what about the kinetic energy? This is where the mass of the electron is going to be substituted, because remember that the moving object off the surface, and we saw this inside the video, was actually a moving electron. So that's half times by the mass of the electron. So I'm actually going to put it in there as mass of electron times by the velocity of that same electron. That velocity is going to be massive. If you get large numbers up, we're talking about tens of thousands of meters per second. It's unbelievable how quickly these electrons actually come off there. I hope that answers that question.
I'm sure it does. Anele, lady, I hope that you are watching. I'm sure she is. She's very good like that. Okay, let me just have a look. You know when your Facebook page slows up again. Guys, please make sure that you do get questions in. I think we literally have 10 minutes left.
Okay.
Okay. Oh gosh, I'm looking. Phil, don't panic.
No, no problem at all. Well, what I'm actually going to do is I'm going to carry on with this while you're finding one of those questions, and I'm just going to elaborate a little bit more, because there is something that you can do with this equation which is quite clever. Sometimes they don't give me the work function, but they give me the threshold frequency. So this W0, I actually gave you a way of working it out. If you had that minimum frequency, W0 is how much energy I need to put in to free things. The way that I calculate that is by finding the threshold frequency and putting it into an equation. Threshold frequency, remember, was a way that I could calculate work function. So I'm going to actually list that in there. There's so many different ways that you can do this. I can find E from HF, or I can find it from HC over lambda. There's so many different ways that we can do this. So I can actually write my photoelectric equation as HF is equal to HF naught. I want you to emphasize that that naught is very, very important. This frequency and this frequency are not the same. This is a frequency of the light which is being supplied. This is a frequency which is the threshold. That belongs to the metal. This is the minimum frequency that I have to vibrate at to get electrons to come off. Please, this frequency and this frequency are so often mixed up. So I'm actually going to make a note on there as soon as we're done here. And we've got our kinetic energy. That remains the same. I think we've covered the kinetic energy in great detail. But if I've got my frequency, this is the light. And so that's the actual frequency of the light which I'm supplying. And this frequency over here is the threshold frequency. Remember that that was a minimum frequency. Now, just talking about the threshold frequency, this was actually shown to you in that little video clip. This was the minimum frequency of light which was needed to get those electrons to leave. Now remember what he had to do. He shone the white light on from the torch and then from that studio light. And very much like the lights which are shining inside here. And we actually found that there was not enough energy. The threshold frequency was not met. This frequency was lower than this frequency, which meant that there was no kinetic energy. Let me just make sure that people actually understand that. The photoelectric effect doesn't always happen. It doesn't always work. If I've got the frequency which is less than the threshold frequency, what you'll find is that there is actually no photoelectric effect. What we're going to find is that the photoelectric effect will not happen. So that's one of the ways that you cannot do the photoelectric effect if the frequency is less than the threshold. However, if you find a case where you've got the frequency which is greater than or equal to the threshold frequency, this means that I definitely can actually do my photoelectric effect. I can substitute, and the electrons should have some kinetic energy. If they're equal to each other, the electron's just going to sit on the surface. If there's extra, it can move to some places. Now, one of the things that they like to ask you in questions is, how do I use this in the real world? Where does the photoelectric effect actually make a difference? Well, strangely enough, the photoelectric effect is the same one inside the camera that's watching me at the moment. This is how the photons of light are bouncing off me, coming to the camera, and the camera is actually using the photoelectric effect to change that into electricity and broadcasting it through to your televisions. So that's quite amazing. I actually find that the frequency of these lights, which are bouncing off me, are exceeding the threshold frequency inside the chip inside the camera. This is amazing. This is how digital cameras, this is how video cameras, like the one that's watching me at the moment, actually work. I hope there's some more questions. Are we looking at one more before we finish?
Okay, I think we can definitely do a few more before we finish. Let's see. Maraping asks, in this question, was the threshold frequency given? If not, how do we calculate it?
Ah, very good question. Okay. All right. Now, in this question, I did not give you the threshold frequency. I was a little bit nasty here. I didn't give you F0.
So there you go. Phil's just being nasty again.
Absolutely. Okay, it's called the challenge question for a reason. Okay. So I want to challenge you. I want to extend you. I didn't give you this guy. If I wanted to find out the threshold frequency, I would have had to give you the work function, or the work function would have had to be available. So what we can actually do is we can work backwards towards a threshold frequency. Let's use the equation which I showed you. So work function is equal to Planck's constant multiplied by threshold frequency. So if I want to calculate my threshold frequency and I've got my work function, I can change this into a different format. I can find that my threshold frequency over there is equal to my Planck's constant, taken across to the other side, which will give me a division. If I take my work function in joules, remember, divided by Planck's constant, I will get my threshold frequency in hertz. Right, I hope that makes a lot of sense.
Okay, yeah, I hope so too. Guys, if you still are not understanding, please let us know. I know Phil sometimes does visit the page periodically the next day to answer some of your questions. We'll see. Maybe he'll be kind to visit the page sometime in the next 2 days.
Absolutely. We're always there to help.
Okay, let's have a look. I think I've almost got so many questions.
Guys have been flooding it.
I know, I'm trying to like pick the best ones here, guys. Okay. What exactly is threshold frequency? I know you've gone over it before, but maybe we can give it a little definition.
Absolutely.
Yeah.
Okay, very, very good question. Okay, now it is often asked as a definition. This threshold frequency, remember that the threshold is a border. It's a line which you have to cross. Now, just the same for metals, I'm going to give you a definition in a moment. That my frequency is the minimum frequency, and here it comes. This is the minimum frequency at which electrons can be ejected from a metal surface by photons. Let me just do that really slowly. I know that there's people at home like furiously scribbling down. The threshold frequency is the minimum frequency required to eject photoelectrons from a metal surface. Let me do that again because there's a lot of complicated terminology inside there. The minimum frequency required to eject photoelectrons from a metal surface. Quite a lot to swallow. Now, in English, okay, I know that that's a whole bunch of science speak and a lot of people are saying, but okay, now I know you gave me the equation and I know you gave me the definition, but what does it really mean? Basically means that this is the frequency which I have to get to in order to succeed in pulling an electron off. I've got to vibrate faster than the threshold frequency to be able to free these electrons from the surface, to actually make these photoelectrons. So the photons coming off me, in other words, these blue photons have to come through to the camera and they have to exceed the threshold frequency of the camera. This is a property of the surface which it strikes. This has almost nothing to do with the frequency over there. This is the frequency coming from the object to the surface. This is a frequency which I have to match or exceed or get above.
Cool. And Jose says, nothing travels faster than the speed of light.
Absolutely. Okay, fantastic. I'm glad that they pointed that out. One of the other famous things that Einstein actually managed to pick out, apart from his famous photoelectric equation, is he managed to figure out that if you start to travel close to the speed of light, it actually becomes more and more and more difficult. The speed of light is considered in physics at the moment, I'm not going to say it's never going to be broken because often that's proved wrong, but at the moment we cannot break the speed of light. It's almost impossible. I'm not going to say impossible because nothing is. But as objects speed up to the speed of light, what actually starts to happen, a really, really weird thing happens, is any extra energy which you put in actually turns into mass. And that's one of his other famous equations. Now, you guys don't need to know this one. This is purely for interest's sake. But because you asked, here we go. I'm sure that you recognize this one. E is equal to, and I'm pretty sure that people at home are busy shouting the end of that equation.
MC hammer.
Oh, not MC hammer.
Not MC hammer.
So E is equal to MC squared. Now that actually shows us that energy can change into matter. As you start approaching the speed of light, any extra energy actually starts to change into matter. So if you're starting to get like crazy velocities for your electrons, that will never actually happen, because most of your extra energy is going to go into extra mass. That electron will actually get heavier.
Okay, fantastic. How much time do we have, producer? Do we have time for one more question? One more question. Okay, this one's from Mbadi. Phil, please, I'm confused threshold frequency with the work function. Please differentiate for me. Is that a quick one?
A very good question.
Okay.
It actually relates to what we're talking about. Okay, I think we've got about a minute or so to answer this question.
Yes, it's going to be quick, Phil.
Now, the work function is the amount of energy. Okay, this is the work which I have to do. I can calculate it from that threshold frequency. Remember that my equation there was E is equal to HF, but this F is a special one. Remember that work and energy are very much the same, because work is the amount of energy which I have to change form of. Now, the work function is the minimum amount of energy to eject electrons. This is the minimum frequency required. This is talking about the frequency of the light which has to come in. This is talking about the work or the amount of energy which I have to give to pull this electron off. Because remember, when you're pulling something off and it's difficult, I have to do work because I'm resisting a force. Hope that answers that question. I think that's all we have time for.
I think that is all we have time for. Mind setters, thank you so much for an amazing lesson. We can do one more question.
Fantastic. Okay, that actually gives us a great opportunity to revisit this. Okay, do we have one more question quick, or can I carry on with this?
I think revisit that.
Okay,
yeah,
fantastic. Okay, now, these two terms are absolutely confused so many times. Work function and your threshold frequency. Remember that your work function was the amount of work which I had to do to pull that electron. Remember where the electron was? It was back inside my metal surface. I actually had to pull it out. So when this electron moves its way out, I do a certain amount of work. Frequency can actually tell me how much work is being done. If I know that I match the threshold frequency, that minimum frequency, I've met the requirements, I'll pass the grade, and that gives me enough energy to do the work function. I hope that the difference between the two is absolutely clear. I think we're just about done though.
I think so, definitely. Mind setters, don't forget that we do have Kathy on tomorrow for life sciences, so you guys better tune in. Thank you so much, grade 12, for a fantastic show. See you same time, same place next week.